Forces in Motion, Chapter 10, Part 5. This relates to Exercise 10E from the textbook. It's headed Connected Particles. Our first example is the typical truck and trailer, car and caravan scenario, something like that. So we've got two particles, two objects on a surface. The surface is almost certainly rough, so you'll have some friction acting on Q, some friction acting on P, labelled Q and P in this particular instance. One of the particles at least will have some kind of forward thrust going on. You'll have a rope or a string between them, which is inextensible and light, or you could have a rod, so you're looking for the forces or the tensions in the rod or in the string. In this particular scenario, we've got Q and P. We have this information here. This is example 1 on page 169. Sorry, example 11 from page 169 of the textbook. P has a mass of 5 kilograms. Q has a mass of 3 kilograms. The friction on P is 10 newtons. Friction always works in the opposite direction to motion. You can see from the arrow that we're accelerating to the right. There is a force on P to the right of 40 newtons, and the friction on Q is 6 newtons. Now later on in the course, you may have to calculate the force due to friction, and you'll be given something called the coefficient of friction, but we're not there yet. The things we have to find in this particular example are the acceleration of the whole system, the tension in the string, and any assumptions that we've made. State any assumptions that we've made. Almost always, when you're finding the acceleration of an entire system, if your entire system is accelerating at the same rate, so in this case the car is pulling the caravan, the truck pulling the trailer, the whole system is accelerating at the same rate. We need to find that. In order to work out the acceleration, we're going to deal with the system as a whole. When we're finding tension, which is an internal force, we then need to just look at one of the particles, either the car or the trailer. It doesn't matter which one, they'll give us the same answer when we start doing the calculations. Before I do any calculations at all, let's label up our diagram. So we're looking at Q. Q has a friction force pulling back of 6 newtons. Q has a mass of 3 kilograms, so we have a downwards force of 3G. We'll have a normal force, which we call RQ. And we have a tension. And the tension will be pulling the caravan forward. So the caravan will have some friction slowing it down, but the tension pulling it forwards. Now looking at the car, in this case it weighs 5 kilograms, it's a very light car clearly. Force downwards due to gravity, 5G. We'll have a normal, which I'll label RP. We've got a force pulling the car forwards, presumably due to the engine in it. It doesn't actually matter in this particular case. So to find acceleration, I'm going to do the usual F equals ma calculations, but I've got lots of forces going on here. Let's take a movement to the right as positive, because that's the direction we're heading in. So let's deal with all the external forces pulling us to the right. Okay, well we got the force of the engine. Take away, I've missed out one of my frictions here, F of P is 10 newtons. So we've got the friction on P and the friction on Q. So the friction pulling to the right is positive. Take away this pulling to the left, take away this pulling to the left. Those are the only forces I have acting on this whole system. One force to the right, two forces to the left. So that's my resultant force. And that has to equal the total mass, 8 kilograms, multiplied by the acceleration. So let's put some numbers in. 40 take away 10 take away 6 equals 8a. Acceleration is therefore 24 divided by the 8. So it's accelerating at 3 meters per second squared. So that's finding A. Okay, part B, let's work out the tension. The tension in the rope. Okay, for this you can either consider this particle or you consider this particle because the tension is the same. The tension pulling this one back is the same as the tension pulling that one forwards. Just randomly, I'm going to choose this one. Again, I'm going to use F equals ma. I have got a force to the right, which is the tension, so that's positive. Take away the force to the left, the 6 newtons, due to friction, and that's equal to the mass, which is 3 kilograms, times by the acceleration. Now I know what the acceleration is. The whole system is accelerating at 3 meters per second squared. So I know that the acceleration of this particle, which is going to be the same as this, the acceleration of this particle is going to be 3 meters per second. So resolve the forces. Force forwards, take away the forces backwards, is the mass, which is 3, times acceleration, which is also 3. So the tension is equal to 9 plus 6 is 15 newtons. The tension is 15 newtons. Now we should get the same answer if I consider this one. So this is considering Q. Let's just do it just to check, and by way of practice, the tension that's slowing P down. Okay, so let's consider what's happening to this particle. Well, let's consider the forces. We're going to do F equals ma. Let's resolve the forces. I have got 40 newtons pulling to the right. That's a positive because that's the direction we're moving in. I've got 2 forces pulling backwards. I've got the friction, which is 10. Take away the tension, which I don't know yet, and that has to equal the mass, 5, times by the acceleration. Well, this thing is accelerating again at 3 meters per second. So 30 take t equals 15, and t is therefore 15 newtons, giving us the same answer. So it doesn't matter whether you choose this one or whether you choose that one. To work out the tension in between, either one will give you the same answer. Okay, the second scenario, which looks very different, but operates on the same kind of basis. Kind of question you might get is the question of a lift or a scale pan or something like that. So here you have a scale pan. In this particular example, it weighs nothing. The scale pan is holding 2 weights, weights A and B, and the whole thing is accelerating upwards. You're told it's accelerating at 0.5 meters per second squared. You're told that A is 400 grams and B is 600 grams. We want to work out the tension in the chain, in the rope here, the force of A on B, and the force of the pan on B. Okay, let's start with the tension. Well, let's resolve our forces again. As ever, I'm going to consider the whole system initially. I've got gravity pulling it downwards. Acceleration due to gravity is 9.8. The force is going to be the mass times 9.8. Well, the mass is 600 grams plus 400 grams, 1000 grams, 1 kilogram. Remember, our units need to be in kilograms. So it's 1 G. I've got tension pulling up. As movement is upwards, let's take upwards as the positive. So considering the forces, I've got tension upwards, take away 1 G. So the force upwards, the force downwards. That resultant force has to give us the mass times the acceleration. 1 times A. The mass is 1 kilogram, the acceleration is what I'm working out. So the acceleration is quite simply the tension, take away 1 G. A, I'm told, is 0.5, so I should really put that as 0.5. Add the 9.8, because 1 G is 9.8, move that over. So the tension is 0.5 plus the 9.8, which is 10.3 newtons. The tension in the rope above the scale pan is 10.3. Okay, now we're looking at the pressure, if you like, of A on B. But that's the same as B on A, Newton's opposite reactions. Let's consider A. What's happening to A? In order to make A accelerate upwards at 0.5 meters per second squared, I need a force which has to overcome the gravity pulling it down and also make it accelerate upwards. The only pressure force on A making it go upwards is the force of B on A. So that's part A, part B. Let's do our resolve our forces again. You've got a force upwards of B on A. It's pushing it upwards. Let's call that the force on A. That's a positive force. We've got a force downwards of A on B. A weighs 0.4 kilograms, so minus 0.4 G. There's my forces. We're just considering the forces on A here. We've got a force upwards, which is the pressure of B, and then we've got the force downwards. So the force acting on A, take away the gravity, because that's moving downwards, is the mass times the acceleration. So the force on A is 0.4 times acceleration. We know it's accelerating at 0.5 plus the 0.4 G. Press a few buttons on my calculator. 0.4 times 0.5 plus 0.4 times 9.8 4.12 newtons. That is the force on A of B and on B of A. And the last bit, what's the pressure of the pan, the force of the pan on B? Well, we'll deal with it in a similar way, but we can deal with these two together. We have got gravity pulling down, we've got the tension of the rope pulling it up. The tension of the rope is the same as the pressure of the pan on B. Well, we know what the tension is already. The tension is 10.3, and the only thing the tension is doing is pushing the scale pan on B. So we know for part C it's the same as part A. And the calculations would all be the same. The tension, in other words the pressure of the scale pan on B, take away the gravity, which is 1 G, equals 1 times 0.5. So it's the working is exactly the same.